All right, welcome back to Computer Vision. We're going to continue our discussion about frequency analysis and how to study images with the notion of frequency components. If you remember last time, we talked about the idea of decomposing images based upon frequency. And we motivated it by showing you this picture. This is that famous Dali picture, which when you allow the high-frequency imagery in there, you see a picture of a woman admiring the Mediterranean or something like that. But when you blur it, that is when you remove the high frequency, you just have the low frequency, it becomes a picture of Lincoln. And this idea of how do we decompose images into thinking about what was going to be a basis set that involved frequency. And the idea that a basis set was going to be some set of functions that were going to linearly span our possible signal. So the idea is that we should be able to make any possible signal out of this set, and that they are linearly independent, so which basically allows me to do this summation. We're also going to end up with an orthogonal basis set, so that when you change the amount of one basis element, you don't get any change in the others. And the basis set that we were talking about was this Fourier set, right? And the Fourier set basically decomposed things into sinusoids, and they were sinusoids here of increasing frequency that were sort of moving vertically and horizontally. And the idea is that we could construct images doing this. So related to that idea was this notion of what we call the Fourier transform. And the Fourier transform was that you would put in a signal, showing it here in 1D, but also talk about it in 2D. And what you would get out was, instead of f as a function of x, that is the intensity as a function of location, you got out a cap f as a function of omega, where omega was frequency. And the idea is that cap f would decompose into an even component and an odd component being represented by complex numbers. And so this would allow us to represent both the magnitude and the phase for a given frequency. And if you wanted to, you could recover that magnitude and phase. The magnitude is just the square root of the sum of the squares of each of the real and imaginary component. And the phase was just this arctan of this relation. To do the Fourier transform, it was represented by this sort of ugly-looking integral. Here I'm showing it to you in 1D. We'll do it again in a minute in 2D. But the idea was you took your function and you integrate from minus infinity to infinity, and you multiplied it by sinusoids of whatever frequency, and sometimes frequency is omega. When we're going to do it for 2 dimensions, it's u and v, so here it's written as u. And even though this does not look like a sinusoid, you had to remember that e to the ik was cosine k plus I sine k. So this is what allowed us to go from the spatial domain to the frequency domain. We also mentioned that you could inverse this if you wanted to, right? So if you give me the Fourier transform, f of u, of a signal, by just changing whether that's plus or minus, I could do the integral and get back the original signal. But now we have both u and v. We also talked about the discrete version, and we showed some examples here where you're taking these sums instead of the integrals. And most of the time, we're mostly interested in the power. Remember the square root of the sum of the squares? And that's represented here. So I might have a signal that has a certain amount of even part and an odd part, or the real and the imaginary. You take the square root of the sum of the squares, and you got the magnitude. And the magnitude of the power is what we'll typically be talking about when we talk about the presence of frequency within a given image. We want to know the power of it. The phase is important for doing reconstruction, but in general, we're not going to be doing a reconstruction. So today, what we're going to do is, in this lesson, is we're just going to relate the Fourier transform to convolution, and in particular, how convolution in space is multiplication in frequency. Let me show you how that works.